So earlier in the week, we studied two types of functions. We looked at rational functions. We looked at radical functions. We looked at how to solve the equations and how to graph them. Yesterday, we looked at exponentials. Okay, both a little bit with graphing, mostly on the calculator, and then a little bit with looking at the transformations as well. Today, we're going to look at logarithms. So I gave you guys an example yesterday of exponential expressions. And that's an exponential equation that wouldn't be too bad to solve. Anyone think they know what the answer would be for x there? 2? Yeah, x would be 3. Good. Now that's not too bad because you can directly raise 2 to a power and get 8. Now, if I did this, now it gets a little harder. Because 2 to the 3rd power is 8. That's too small. 2 to the 4th power is 16. That's too big. Now the answer is somewhere between 3 and 4. So how are we going to solve for x without a graphing calculator? Okay, we could put this in y1, y2, and do an intercept. But there's a much easier way to do that. And that's where logarithms come in. Right? So logarithms are the inverse of exponential functions. Just like squaring and square rooting are inverses, exponentials and logarithms are inverses, meaning they can undo each other. So whenever we have variables in the exponent, a logarithm is going to be what we have to use to try to solve it. So in algebra 1, you talk a lot about the vertical line test. And the vertical line test is used to tell you if your graph is a function. Well, there's also something called a horizontal line test. And the horizontal line test is used to tell you if the inverse of your graph would be a function. Keep that in mind. Horizontal line test is used to tell you if the inverse of your graph would be a function. Now, I will tell you, because if you think about an exponential function, it looks like this. If you put a horizontal line, would it ever hit that graph more than once? No matter where you put it. No, never hits it more than once. That means exponential functions pass the horizontal line test. All right, now let's try to put this together. Exponential functions pass the horizontal line test. Logarithmic functions are the inverse of exponential functions. So if an exponential function passes the horizontal line test, what do you think that means about log functions? What test would they pass, since they're the inverse of exponentials?
Vertical line test.
Exactly, good. They would pass the vertical line test. Exponential functions pass the horizontal line test. That means their inverse would pass the vertical line test. So that means logarithms are functions. They will pass the vertical line test. And if you want to think about what that means visually, okay, inverse functions are what we call reflections over the line y equals x. So let me graph a log function, and let me graph an exponential. And you can see how they're inverses. Now, one thing we have to be a little bit careful about is when the calculator sketches a log function, it can't do it properly. That's how it's going to look in red when you sketch a log function. This is how it should look. In blue, that is an exponential function. In red, that's a logarithmic function. If this was a piece of paper, I could fold it right on that black line. The graph in blue would land directly on top of the graph in red. And that means that they are mirror images of each other. So think back to exponentials. And Leanne, what kind of asymptote did we have in an exponential function? Yes, we had a horizontal asymptote in exponentials. So what kind of asymptote do you think we're going to have in logarithmic functions? Because they're the inverse. Yep.
Vertical.
Good. You're going to have a vertical. Okay. So this graph in red does have a vertical asymptote. Might look like the graph in red has a horizontal, but it doesn't. The logarithmic function keeps growing very, very slowly. In fact, let's say you look at your table, and let's put in a log function and just see how slowly it grows. Let's go to my table. Okay, this is some data we had from yesterday, but what do you notice about trying to plug a negative number into a log? Yeah?
Provides non-real answers.
Yeah, you get non-real answers, so we're not even going to worry about negative numbers with logs. I wasn't going to bring that up yet, but we have data in the calculator from yesterday that pretty much shows you can't take the log of a negative number unless you're dealing with imaginaries. Okay, so we're just going to focus on positives. Yeah?
What if you shifted the logarithm to the left?
If you shift it, then you could do some negatives, but there would be a point where you'd have to stop because you can never let the argument to a log be negative. Yeah, that's a good question. All right, so watch what happens if I plug in, say, 20. Then I'll plug in 200, plug in 2,000, and then I'll plug in 50,000. Look at how slowly the y values are growing. When I let my x value go all the way to 50,000, my y value was only about 4.7. So think about that. You've gone all the way to 50,000 on the x-axis, and you've only gone up less than 5 units. So logarithms grow extremely slow. They grow just as slow as exponential functions do fast, because they're inverses. All right, so this is how you write a logarithm. And let me show you if this was like a piece of lined paper, what it would look like. The y, the equals, the log, and the x would all be right on the line on your paper. The a is a subscript. It would be below the line. Okay, there are no exponents anywhere in that expression. Some people think because the a is lower, oh, and the x is higher, the x is an exponent, but the x is actually right on the line. If you did this, now you have an exponent. Okay. There are no exponents in there at all. And the way you pronounce that is y equals log base a of x. Y equals log base a of x. And x is called the argument. The argument is what you are plugging into the log function. So when we do a square root, technically you could call 10 the argument. It's what's being plugged into the square root. Does anybody remember what we actually call the argument to a square root function? It has its own special name that begins with an R.
Root.
So the root is the actual symbol. We've got the radical symbol. But what about the thing under it? Remember? Yep, Caleb?
Is the radicand.
Good. Nice job. It's the radicand. So we normally call that the radicand, but you can also call it the argument. It's just the thing you're plugging in. There are two logs that have special names. One of them is called common log. The other one is called natural log. Common log is when you have a logarithm with a base of 10. So for example, if I said to you on the test, find the common log of 7.5. You press the log button, 7.5, and you hit enter. The calculator didn't put in a base. There was no base written on that log. You can put a base on it, but it didn't. Because there was no base, we assume that it's the common log. And so if you ever see something like just log x, you can always assume that that is the common log. Now, like the argument, the base also has to be a positive number. So with logarithms, you're never going to see a negative base, and you'll never see a negative argument. If you do that, you're getting into imaginary logs. And that's not something we're going to look at. Okay, any questions on that so far? Everybody have a chance to copy that? So the other special log that we can have, we talked a little bit about this number yesterday. We didn't go into depth with it, but it's if you have a base of e. Anytime you have a base of e on a log, that is called the natural log. Common log and natural log are the only two logs that have a special name. Other than that, we just say a logarithm with a base of, and we just say the number. You want? All right, so logarithm, special names, common log, natural log. There are no other special logs. And those are the only two logarithms that you can put in on a calculator. You have a button for common log, and you have a button for natural log. Okay.
The log with a specified base under that.
So there is a way on some calculators that you can change the base and put in a different one. Most of the time, I'm going to have you use a formula, and I'll show you how that works. All right. But there are some calculators that allow you to change the base. Not a necessary feature to have, because I'm going to show you the way to get around that. Yeah.
So what would be the natural log of e?
We'll talk about that. Once I show you a little bit more, I think you'll be able to answer that question. But I need to show you some formulas first.
All right, cool.
But yep, we can talk about the natural log of e. It's a good question. You might have noticed when I pressed the natural log button, it wrote this lowercase l, lowercase n. Well, lowercase l, lowercase n is a short way of writing log base e. You actually never see log base e written. People always use this abbreviation, lowercase l, lowercase n. Why isn't it lowercase n, lowercase l? I don't know. That would make sense, natural log and l, but they do ln. So the one thing you've got to be careful about with this notation is some people forget the base because it's hidden. When you write ln, the base is absorbed into that ln, and the base is e. So you have to remember that. The base becomes hidden. So any questions on the abbreviation for log base e? Yeah.
Would it be wrong to write it log base e, or is it just like redundant?
No, you could write it that way. Yeah, that would be okay. Again, you're never going to see that on a test from me or in a book, like our book, but you could. All right, if we go back and look at this red graph again, Where was it? Maybe it's underneath. Uh-huh. So if you look at the graph in red, we said earlier that there's a vertical asymptote. That means the domain stops somewhere. And we already basically said what kind of numbers you can use. What does it look like the domain is for that graph in red? Yeah?
0. No. Yes. 0 to infinity.
Including or not including 0?
Not including 0.
Not including, because it's a vertical asymptote. So domain is 0 to infinity. And what about the range here? How low and how high does it look like that graph goes? Yeah?
Negative infinity.
Yeah, the range is negative infinity to infinity, even though it's going up at the slowest possible pace any graph could ever go up, basically. It will go up to infinity. Okay. And those two ideas are summarized right there. Domain, 0 to infinity, open interval. Range, negative infinity to infinity. All right, so one of the formulas we're going to use quite a bit allows you to convert between what I call log form and what I call exponential form. Let me click ahead a few examples so you can see like what I call log form and what I call exponential. That's log form. That's exponential form. Exponential form has an exponent. Log form has the word log. Right? And we're going to convert between the two. So remember, when we're dealing with exponentials, we don't let the base equal 1, because we talked about 1 to the x would just stay as 1. And we can't let the base be 0, because when you're dealing with logarithms, both the base and the argument have to be positive numbers. So converting between log form and exponential form is really a matter of rearranging. It's not really a calculation. You have to look at where things are on the left and where they move to when you change the form. And the way I remember it, first thing you always want to remember about a logarithm, logs are exponents. Anytime you use a logarithm, you are trying to calculate an exponent. So if I type in log of 7.5, I get 0.88. That 0.88 is an exponent. An exponent on what? Well, I don't know what the problem would have been that caused me to have to do that. But the answer is an exponent. So logarithms always give you an exponent. That's why if you look at this, the logarithm equals an exponent. So notice when you rewrite it in exponential form, the y becomes the exponent. So logarithm always equals the exponent. The next thing is this. What did we call that number that I just, well, the number that has the blue box around it? When you pronounce that, the A is your what? Yep. It's your base. Well, when you rewrite something as an exponential, it also has a base. The base on the log becomes the base on the exponential. So the logarithm equals the exponent. The base on the log becomes the base on the exponential. And what did we call this? The thing you plug into the log. Yeah?
Argument.
The argument. And what happens if you argue with somebody all the time? Or you argue with everybody you know?
People don't like you.
People don't like you, you're going to end up alone. If you argue, you're going to end up alone on one side, all by yourself. All right? So the argument ends up alone. And that's it. You just have to try to remember those three things when you're rearranging it. So let's try this one. I want to convert this equation into an exponential expression. Let's start with the 3. What is the 3 called again? That's my base. So that's going to be my base when I rewrite it. Logarithm always equals what kind of number? Exponent. So the y becomes my exponent. And what's going to end up all by itself? X, because that's the argument, and it annoyed everybody, so it ends up alone. Now, there's nothing you can solve in that problem because you don't know y. If you knew what y was, then you could do it out. But that's all they're asking you to do. So that's changing from log form to exponential. All right, let's try it the other way. Let's change from exponential to log. Well, if you're writing something in log form, what do you think the first thing you have to write down is?
Log.
Yeah, you have to write the word log. Logarithm always equals what kind of number? Exponent. What's my exponent in this one? 3. Now I need the base on my log. What was the base on my exponential? 1.2. So 1.2 is going to be the base on my log. And now what do we call the thing that was all by itself? That's the argument. And that's what gets plugged into the log. So you're taking the log of m with a base of 1.2. Right now, we wouldn't know how to type that in. I told you the calculator only has 2 buttons on it, regular log and natural log. So the calculator can do base 10 and it can do base e. If you want to do bases other than those, I'll show you another time how you do it. Okay, questions on that one?
Are you just gonna give us bases of E and okay?
If that's all we get to today, then that's all that would be on the test.
Oh, I found it. It's under math.
Yeah, it's
Log base.
How about this one? Caleb, what's my base here?
E.
E. And Madison, logarithm always equals what kind of number?
That.
And what's my exponent in this case? B. And Sophie, the 9 is my
It's like the argument.
the argument. How can you write log base e of 9 in a shorter format? That's not something you'd probably ever see. John? ln 9. Now that's something, we could just type it right in on the calculator. We could press ln 9, hit enter, and get the answer. But that wasn't the direction. The direction was just to change it to a log expression. And we've done that. Technically, if you left it log base e of 9, you would still be right. This is a little bit simplified. Okay, questions on that? Okay. So let's show that these two things are the same. There's only one thing we know how to do with logs right now, and that's change it to exponential form. So let's change this to exponential form and see what happens. Michael, what's my base?
2.
2. And Nick, logarithm always equals what kind of number?
Logarithm. It's a 3.
What kind of number is this again? This logarithm equals the
Exponent.
exponent. So my exponent is 3. And Annalise, what ends up by itself?
E.
The argument. Which is 8. Is that true?
Yes.
Yeah. So we have shown that log base 8 of 2 equals 3. Just by rewriting it.
You mean log base 2 of 8.
Log base 8 of 2 equals 3.
Wait, so you say the argument instead of the
Log base 2 of 8 equals 3.
Okay,
Yeah.
That was very confusing.
Yeah, log base 2 of 8 equals 3. Sorry,
Okay,
I was
yeah.
looking at it the wrong way. Any question on that? Log base of 2, and then that's your argument. Log base 2 of 8. That's how you say it. All right, let's try this one. What's the only thing that we could try to do with this and then see if it works?
Put in exponential.
Put it in exponential form and see what happens. Can anyone tell me what that would be in exponential form? John?
It would be, is it 5 to the x is equal to 125?
Okay. Now, think about what kind of number x would have to be to give you a fraction. If it was 5 to the x equals 25, then I would go with 2. But this is 5 to the x equals 1 over 25. So how are we going to make it 1 over and get that in the bottom? Yep.
-2.
-2. Perfect. So the answer there is -2. Now, if this was a 26 or a 27, we're going to be stuck. We wouldn't know how to do that yet. I'd have to make it a power of 5 for now. Questions on that one? All right. Let's try this one. Only know one thing to try, so let's try it and see what happens. Lindsay, could you tell me what this would be when I rewrite it?
X equals 5 to the 1.5.
Yeah. And you could just type that in the calculator and get the answer. So 5 is your base, logarithm equals the exponent, and the argument ends up by itself. Okay, so that's an example where the variable was the argument. Let's look at an example. I think I have one where the variable is the base. How would I rewrite this one in exponential form? Tim?
X to the power of 2 is equal to 3.
Good. Now, you can't solve that by adding, subtracting, multiplying, or dividing. You've got to get rid of the square. How do we get rid of the exponent of 2?
You square root both sides.
We square root both sides. And remember, x is a base. We talked about the base. It has to be greater than 0. So normally when you take a square root, there are 2 answers. But you cannot use the negative answer with a logarithm. So x equals square root of 3. Questions on that? All right. Let's look at some special properties of logarithms. So these are more like patterns to look for. They're not really a calculation you would do. And we'll do some examples after. But if you ever ended up with something that was a to the log base a of x, the answer that you would get when you simplify all of that is whatever number is right there. So if you had like 3 raised to the log base 3 of 12, the answer there would be 12. It's a special pattern that when these two numbers are the same and the logarithm is up in the exponent, basically this part cancels out and you end up with just what's right there as your answer. Now I'm going to explain why that's true on a couple of the other ones. We're going to look at 4 properties. I could explain it on this one as well, but I'll explain it on the next 3 about why it works. Let's look at this one. So this one says if you have log base a of a to the x, and you have to simplify it, the answer is going to be whatever number was right there. Now, let's see why this one is true. You really have 3 things here. This, let's do different colors. This, and that. What is, well, first of all, is this a log equation or an exponential equation? What is it?
Is it both?
No, it can only be one.
Log.
It is a log. Anything that fits this pattern, I don't care what you put in the boxes, that's log. Even if one of the boxes has an exponent in it, it's still log. Okay? Let's rewrite this in exponential and watch what happens. what's my base here? Or tell me what color box the base is in. Yeah, that's the green box, just because there's lots of A's and X's, so I'm trying to be clear. The green box is your base. A. Logarithm always equals what kind of number? What the blue box would end up turning into your what? Your exponent. And what's going to end up by itself on the other side? A to the x.
That's crazy.
Is that true? Yeah. This is really the reflexive property. It's just written as a logarithm. We always know from algebra that something is equal to itself. Always. This is writing that rule as a logarithm. Yeah.
So the natural log of e would be 1 because e to the first power is equal to 1.
So if you were trying to figure that out, that would really mean when you rewrite it, e is your base, x is your exponent, your argument ends up on the other side by itself. So e to what power gives you e? Yes, you are correct. It would be 1. Let's look at property 3. Property 3 says that the log base a of a equals 1. So in other words, log base 2 of 2 is 1. Log base 10 of 10 is 1. Let's change this one and see why this one's true. Is this log form or exponential? Log. What's my base here?
Red.
The red one. The red A. A is my base. Logarithm always equals what kind of number? Exponent. So the 1 becomes an exponent. And what goes on the other side? The blue box, right? That's your argument. So what rule 3 is saying is if you raise anything to the first power, you get itself. Again, another basic rule from algebra. Anything to the first power gives you back what you started with. This is just writing it as a logarithm. This is how you would have seen it in Algebra 1. Okay, so there's very simple reasons behind why these are true. And let's look at this one. Log base A of 1 equals 0. They're all different here, so I don't really need colors. If we change this to exponential, what's my base? A. What would be my exponent? 0. And the argument in this case is what? 1. So that ends up by itself on the other side. That's the rule that says if you raise anything to the 0 power, you get 1. Again, that's another rule from algebra. Anything to the 0 power is 1. This is how you would have seen it in Algebra 1. This is how you can write the same rule using a logarithm. Okay, so questions on those special properties? All right, so let's try a few examples. And this says simplify 2 to the log base 2 of pi. And they want you to tell what it's equal to. Which property does that one look like? 1, 2, 3, or 4? Yeah, that's property 1. So based on property 1, what would be the answer if you simplified that? Pi. The answer is whatever the argument is at the top, right there. Pi. How about example B? Log base 0.2 of 0.2 to the negative 4th.
2.
Yeah, that looks like property 2. And using property 2 to simplify it, what would you get?
Negative 4.
Negative 4. So again, there's really no calculations you're doing here. You're looking for a pattern, and you're finding which formula it matches. And that's it. Let me scroll down. How about C? Which property does that one look like?
2.
It is 2, but could we make that a little clearer?
Just write log e, or log base e of e.
Yeah, rewrite this instead of the short way, write it with its long form. Log base e. ln means log base e. And then put the rest of it. Now, it looks exactly like example 2. What would the answer be when you simplify?
KT.
KT, whatever k times 2 is. Okay, I didn't have one for the other ones, I'll just make up one more. What's log base 12 of 1?
Zero.
0. That's property 4. Okay, so these are just a few tricks that we can use to simplify logarithms in special cases. Any question before we look at the last thing for today? All right, so the last thing is how we can take logarithms that are separate and combine them, or take ones that are combined and split them. So it's kind of like combining like terms. And there's 3 properties I'll show you. The first one has to do with a log of a product. The log of a product can be split apart into a sum. So when the argument is a product, you can split it as a sum. The first argument is the first factor. The second argument is the second factor. And the base stays exactly the same as what it was originally. So there's an example with numbers. If you have the log base, and again, this a could be any base, 2, 6, 10, e, so you can do this with ln's. If you had log base a of 4 times 5, that would equal log base a 4 plus log base a 5. Let me show you that on the calculator, and I'll do it with base 10. Log of 4 times 5, which is just 20. Now, look at log 4 plus log 5. It's exactly the same thing. So this gives you a way to take, depending on how you look at it, a sum of 2 logarithms and combine them into a product. Now, if a product turns into a sum, what do you think a quotient would turn into? Michael?
Subtraction.
It would be subtraction. Here the order is important. Log base a of a fraction, we do log base a of the numerator minus log base a of the denominator. I'm not going to go through this example with numbers, but if you want to try that on your calculator with base 10, you could do it. Yes?
Would log a4 minus log a5 also be equal to log base a of 4 divided by 5? Like if you did that out, like if you took 4 divided by 5 and just skipped that and did log base a of 0.8?
Yeah, you could change this to 0.8. If you did log base a of 0.8, it would be the same as log 4 minus log 5. Yep. Most of the time, it's more convenient to take something that's separate and combine it together. That's more useful. But we'll practice both. And the last rule, and then we'll do some examples, and that'll be it, has to do when you have an exponent on an argument. What you are allowed to do is move that exponent in front.
So would that be 5 times log base 10?
That would be 5 times log base 10 of 3. So let's see why that's true. That's actually pretty easy to show. What does 3 to the 5th really mean? 3 times 3 times 3 times 3 times 3. Now, this is exactly the same as rule 1. You could have m times n times k times z. You can have as many as you want here and just keep splitting it into sums. So all of these would split into one sum. Well, many sums. Log base 10 of 3. That's the first one. Plus log base 10 of 3. There's the second one. Log base 10 of 3. Here's the third one. Log base 10 of 3. Log base 10 of 3. How many log base 10 of 3's do I have?
5.
5 of them. So that's 5 log base 10 of 3. That's why you can take the exponent and move it in front. It's really just rule 1. It's like a special case of rule 1. And then from algebra, what did we say yesterday? I think it was yesterday or maybe the day before. When you have a square root, that's the same as raising something to what power? 1/2, yes. And that's important because if I give you a problem like this, and I say rewrite so there are no exponents in your final answer, and you leave something like this, I would mark it wrong. You might say, well, there are no exponents in that answer. Yes, there are. There's a hidden exponent of 1/2 right there. So with something like that, that's what it really means. And rule 3 allows you to take that exponent and drop it down in front. Okay, so remember, anytime you have a square root in an argument to a log, you do have an exponent that's hidden. And you would want to put it in front. That's what I would be looking for a problem like that. All right, so let's try a few combining and separating problems, and that'll be it. Okay, so this says separate into multiple logarithms, express powers as factors. What that basically means is don't leave exponents in your final answer. Put the exponent down in front if you have one. Okay, so this is a product. Is that going to split as a sum or difference? Sum. So we're going to have 2 logs. What's going to be the base on each log? 4. 4. My first argument. Second argument. Done. That's all there is to it. Let's try another one. Log base 2 of 5r cubed. Is that going to split as a sum or a difference? That's a sum. 2 logs. Base on each log? 2. What is my first argument? John?
5.
And my second argument?
3 log 2r.
So it would be r cubed, but it specifically said in the directions, do not leave the exponent in the answer. It said make it a factor. That means make it multiplication. Put it in front. So the r cubed ends up with the 3 in front.
The commutative property is still there, right? Like log base 2 of 5 plus 3 log base 2 of r is the same as the inverse, right? Like 3 log base 2 of r is equal to
Yeah.
Yeah.
You could have that order switched. Yep. Just like you could say 5 times r cubed or r cubed times 5.
Yeah.
Same thing. All right, let's do this one. Is that going to split as a sum or difference? That's a difference. What's going to be the base on each log? 9. 9. First argument. Second argument. 2. Great. Let's try this one. So we did log base 4, log base 2, log base 9. Now we're doing log base e. You don't have to write it as log base e, though. You can use the abbreviation. Anyone think they could give me the final answer for that whole thing, Tim?
3 ln y minus ln 8. 8.
Good. So 3 ln y minus ln 8. Okay, so any questions on that? So that's taking one logarithm and separating it. Now let's try a couple where we reverse it. Take something that's separate and put it all back together. Okay, so just do everything backwards. What would be the first thing that you would do to put this back together? Yep.
4 log A. 4, sorry, yeah. So it would be, was it log A to, log base A of 3 to the 4th.
Yep. So the first thing that you do is put the 4 back as an exponent. Now, we could just might as well do that out. What's 3 to the 4th power? Caleb? 81. Now, how are these logs going to combine together? As a product or quotient? It's going to be a product. What's going to be the base on my combined log? A. And what's going to be inside the parentheses? 7 times 81, which is 567.
So you don't want us to include exponents in the final answer?
No, because they said to put factors as powers, and then you have to do the power out.
Okay.
Yep. I think we had one more we might as well do. Alright. Let's start with the 2/3. What's going to happen to the 2/3? That's going to be an exponent. That's going to be easy to do in your head. I'll show you how. Now, let's see. 3 to the 4th. You know what? Let's just change this because I don't want that to come out. Can't have 0. Let's make it 71. What was 3 to the 4th? We just did that.
81.
What's 81 minus 71? 10. Now, ln of 8 to the 2/3. The way you can think of that, when you have a fraction, 2 is your exponent, divided by 3 is your root. What's 8 squared?
64.
Divided by 3 means cube rooted. What's the cube root of 64?
4.
4. You could always type that in on a calculator, but this is one that's pretty quick. All right. When I combine them into a single ln, how is it going to look inside the parentheses? Mike?
ln 2 divided by 5.
Yeah, I'll do it in 2 steps just so anybody watching understands what happened. You put them in as 4 over 10, and then he reduced it correctly to 2 over 5. All right, so that's combining and separating logs. So a lot of the questions in this section are very fast. Okay, they're very, very quick questions like that. All right, so let me put up the homework. And what I'll do after you guys leave is I'll take a quick look at the test. Maybe I'll start doing it right now. And I'll put a list of topics that are on the test. And I'll make sure I put that in the end of the video. All right. And these are the topics that will be on the test tomorrow.